Good evening, everyone. So today I want to present a paper which is famously named speculative decoding. So has anyone maybe here, you can, I think, raise hands online. Has anyone heard about that paper or I would say that method before? So it's actually a method that was created by Google DeepMind. And the goal is to accelerate LLM inference. Most providers that you know of, OpenAI, I don't know, 𝗂𝗏𝗃, Grok, these kind of providers, they all use that technique under the hood. So today we're going to talk about it. So I just saw one hand raised, which was Louis. So good time to discover this technique. So actually the title I decided to take was the inference free lunch, because when I read the paper first, I was kind of shocked that this looks to me like free lunch, that usually we say there is no free lunch, but with speculative decoding, I found that there is. Just a reminder on how LLMs generate text. I think you are all familiar with that kind of representation, that LLM generate text in an autoregressive fashion. So generating, here I represented word after word. In reality, it would be token after token, but you get the idea. So generating one word at a time. In the paper, they make two observations. The first one is that some tokens are easier to generate than others. So if you take my example here, for example, at the third step, at the cat-sat on, I mean, when we have to predict on, it's quite easier than what follows the, because the can be followed by a lot of things, whereas the cat-sat has no, doesn't have a lot of possibilities. There is the same sense of easy generation when we talk about code generation, for example. In Python, if I say for, usually you will have something like I followed by the for word. So this is the first observation that they make. And the second one is about the memory bottleneck in transformers. So they show that the hardware that we have today, so GPUs, TPUs, can basically handle trillions of bytes, like hundreds of trillions of bytes per second, whereas the memory bandwidth is only in the range of a few trillions of bytes. So there's definitely a bottleneck on that part, and especially in the case of transformers, they show that the transformer can handle 1 to 10 flops per byte read. So there is some unused compute that we are left with. So from these two observations, they wonder what they can do to accelerate the inference. So the main idea is, why can't we try to compute several tokens in parallel at a time to make use of this pair compute that we have? So just to give a quick introduction, because their idea doesn't come from nowhere. Actually, it is inspired by what we call speculative execution, which comes from computer science. So if I had to explain very easily what speculative execution is, basically, you would perform a task, but at the moment you start performing this task, you are not aware whether it is needed or not. But you just start it nonetheless. And so afterwards, when you get the information that the task was needed, then you're happy because you have started it already. And if it was not needed, then you can just abandon everything. So I make a quick example here. So if we assume we have two lengthy operations that we represent with functions f and g, we denote by y the output of f of x, and by z the output of g of y. And so basically, what we would do if we were in a sequential fashion, we would basically just start from x and compute y using f. And then once we have y, we use G to compute Z, right? This is what most people would do. But with speculative execution, you introduce a new function f star that is an approximation of f. And so the idea is that from x, you will use f star instead to compute a y star variable. And then you will use that y star to compute a z star using G. So here it's still sequential, but the first step is very likely to be faster. And so in parallel, you can also use f. So I'm representing it with a very long arrow to represent the duration that is involved to compute the real y. And so once you have computed both steps in parallel, you would basically try to compute some kind of distance between y star and y. And if you're in a reasonable range, you would assume that z star is enough, right? And so you have gained some time in your execution. So this is the main idea on which speculative decoding is based on. By the way, you can always interrupt me if anything is unclear. They also introduce what we call speculative sampling, which is basically the same as what we've seen before, just that the functions f and g, instead they output a probability distribution, right? So when I say outputting a probability distribution, I think you can get where I'm heading to, because you might know that transformers actually produce a probability distribution over the vocabulary of tokens. I mean, the language models. And yeah, just a quick poll so you can answer in the chat. Do you have any idea what could be, in that case, a faster approximate process than F? So let's say it's our big transformer. What could be F star? So an approximate faster process in our case. Do you have any idea? You can say it in the chat or even raise your voice. Random, okay, could work, but would have terrible performance, right? But that's a good idea. We can talk about it later, I think. So just a few seconds before I give the answer everybody wants. So, okay, no more tries, no more guesses. So actually, you can just use a small LLM. So closer to a random function, but not random yet. So instead of using the big 400B model, maybe you can use a 7B model, right? It's approximate to have a modelization of the probability distribution of your base LLM, but it's faster. So the researcher at Google DeepMind start from this idea. And here I'm going to give you a little more detail about their algorithm they use to generate text. So here, the F star model is a very small model. So you can think of it as, for example, 100 million parameters, something like, or a very small model like GPT-2. And so they would generate first a number n tokens with F star using the autoregressive fashion that we have seen before. So this we cannot avoid. And then this is the key idea of their paper, is that they will batch all those n generated tokens to use the big model to verify them, but in parallel. And so they obtain two distribution of probabilities, one created by the draft model, which is the small one, and one created by the target model, which is the big model. And so if you take a look at those two first steps, actually, what compute do we have? We have generated n forward pass with F star, which is a very small model. And we have computed one forward pass with F, but as a batch. So maybe a bit smaller than one single forward pass. And then they have some heuristic based on f of x and f star of x, where they discard or keep the generated tokens. So it's kind of a review process made by the bigger model. And so they have a rejection sampling method. where they would stop to consider the token generated by the draft model, the small one, after the first rejection, and just generate right over. So just to make it a bit clearer, I will give some more details. So let me just switch that. So this is about the design. Maybe we can go over it a bit later, but they have this kind of formula where they take a division of both probabilities, and then they have this custom probability distribution that they build out of the two first. And I think the most important thing is the result that I put here, is that with this heuristic, they can prove mathematically that the sample x in the end follows the same distribution as if it was sampled from the main model. So what does that mean? That means that with one forward pass with your big model and n forward passes with the small model, you can basically just get the same distribution as if you had made n forward pass with the big model. So a clear free lunch. But it's not that free, actually, because so the results first, they take a 11B model as target, and they take T5XXL, so a fairly small model right now. At the time it was big, but right now it's very small, as draft model. And they show that keeping the same distribution probability as the 11B model, they achieve a 3 times speed up on generation. So impressive results. So I told you that there was a free lunch, but you might notice that actually there is a cost involved because we have to keep in memory two models. So the trade-off here is that we have to host both the draft model and the target model, even though the draft model usually is very small. So it's a little, very little cost. And so this is what this slide is, why this slide is called self-spec-deck. So there is actually a new method that was implemented, which is the following. So we have this little trade-off with the memory. How can we find a solution to it? So to make it simple, you might know that a transformer is actually a stack of several transformer blocks. So a transformer, basically, you would have a lot of different layers with the same architecture, and the output would pass from one to another. And once we reach the end layer, we would have what we call the classification head that that predicts what is the next token, right? And so the idea for self-speculative decoding is that you can actually stop at the second layer, for example, and plug the classification head right away without going through the third layer, because all of those transformer layers, they have the same output shape. So self-speculative decoding means instead of taking a draft model and a target model, you actually extract a draft model from the target model itself, right? By just stopping at an intermediate layer. Obviously, the earlier you extract the classification, the worse your result will be. So there is a trade-off between the speed of compute and quality. But this is a way that you can, this is also a way that people use regular LLMs to make them faster. In the end, they can also just plug the classification head to an intermediate layer. And so with this modelization, we achieve what I really call the free lunch, because we do not have any memory constraint added on top of that. And we can achieve speed ups that I've shown before. So ×2, ×3 speed ups. And the last thing I want to talk about is what are the parameters involved into these trade-offs, and how do we define the speed of iteration? So there are two things. The first thing is the window size. So we have denoted it by n or gamma in the paper also. So this is the number of tokens that your draft model will draft, right? Obviously, there is also the acceptance rate, which they call beta. So it represents how close your draft model is in performance to the target model. And so usually, if you have a very poor draft model, you would go for a smaller window size because you don't want it to predict too much tokens because it's very likely to fail. And so at the contrary, if you take a very good draft model, you can have a broader window size. And then the target model will verify more tokens at once. And so there is this trade-off, but usually they show that they can reach very impressive speedups, sometimes up to 5x. And so this is a reason why it's actually implemented in most inference platforms that you might know of. And so just to finish on, maybe I think a video is the best thing to finish with. Let me show you. So I will just share another tab, which is actually, let me see that, which is actually from Google DeepMind themselves. So they really have this cool website on speculative decoding. And so first is this GIF. They show the before and after, because it's actually implemented in their own version of Google search. And so let me reload that because I think, yeah. So on the right is speculative decoding, and on the left is no speculative decoding. You can see that the output is exactly the same. I think because they might be using greedy decoding here, they have the same output, but it's some kind of proof that we have the same probability distribution. So very good use case. And then also, let me show you that. So this is a visual explanation that they make of how it works. So let's wait for it to restart. So as you can see here, the model generates several tokens at a time, and some are discarded, some are kept, depending on how correct they are. And so with this animation, you can see how visually, it's way faster to use this technique. And especially in that case, self-speculative decoding would imply that we don't have this very small model, but only the big one, and that we extract the drafts from intermediate layers. So I think that was the main point I wanted to make. I suggest, if you're interested, you take a look at the paper, which is this one. Let me reload that. Fast inference from transformers via speculative decoding. And there is a lot of actually mathematical things involved. So they have theorems, definitions, and so on. Very cool plots. Also, they show here the time reduction, for example, in wall time. That is a lot. And here you can see, and I will let you read about it, but the mathematical proof that we have the exact same distribution. So it takes a fairly long time to read because I felt like it was not easy, but I encourage you to do so because it's clearly, every time I read it, it's very still surprising that we get this result. Yeah, so that was basically what I liked about this paper, and I hope you enjoy this presentation. And if you have any questions, feel free to do so.
Thank you so much for your presentation, Raphael. I really loved it. It was really visual with all the drawings, high quality. And I was really curious if you have knowledge of this technique being applied to other models than LLM, for example.
Yes. So actually, I think they wrote it just, let me see, just here. So they say that it's applied to domains such as image and speech generation. So we can follow these links, I think, to get the papers involved. But yeah, definitely. So this would be for speech synthesis. This one, I think, for image generation. But it definitely makes sense that you can use it for a broad range of use cases.
Thank you. And I forgot to tell you what we were on time, but you
Yeah, I
were
think
on
we
time. That's
were,
perfect.
yeah, perfect. And also, maybe a last note, which I found interesting, is that you can also improve speculative decoding performance, which means making it faster if you make some distillation between your target model and the draft one, because obviously the goal of distillation is to make both probability distributions alike. And so they show that in the paper, the more closer the distributions are, the more likely you are to accelerate more your inference. And so, yeah, also, I think there's definitely a way. I don't know if people came up with that already, but I definitely believe there's a way to apply that to even diffusion models, this kind of things. I think we have a question from Alex.
Yes, hi Raphael, nice, thanks for the presentation. So I always try to think in how we humans think and how that sort of transfers what we do there in sort of for us. And I feel like the version 1, where we don't have speculative, so autoregressive is like, I have to write myself a text every single word, sorry. And in other times, I basically have a digital, like a twin of myself, which is not as smart as me, but
Yeah.
is basically spits out propositions of what I should write next, and I either say, oh, that sounds good, or that doesn't sound good, and that's why I'm faster, because I don't have to rely too much on my thinking rather than relying on what's. I think that's how I would sort of transfer it to how we think. What do you think about that?
Yeah, definitely. I mean, it would be like if you value more your time than maybe your little brothers, and then you force him to write your essay, and then maybe you correct the things. But I believe most people can do that also with ChatGPT itself. Like, I mean, as far as I'm concerned, I would ask him to write something, but usually I'm not convinced by the whole package, and then I would just review it and make it kind of mine, I would say. So I think we are all doing some kind of speculative decoding under the hood.
Yeah, yeah, cool.
So I have a question. Thank you for presentation. I'm not specialist about LLM, so I don't know if my question. So there was small model and big model. Do you think we can add smaller model or bigger model later, like the size model?
So can you repeat your question, Min? I think your microphone, I was not able to hear very well.
Sorry. So you said that there is a small model and big model, and they are kind of working together.
Yeah.
And do you think we can add third model, like more smaller or more bigger model?
Oh yeah, so actually that would be very interesting. So you would think kind of a 3-layer speculative decoding. So that would actually make sense. So maybe we could think of a very, very small model generating very big ranges. So let's say 50 tokens at a time, and then intermediate one maybe verifying it, and then based on some algorithm, the big one would only verify it in some cases. I think it could make sense, definitely.
Okay.
Yeah. Yeah, that's exactly what Alex said, nested speculative decoding. I'm not aware whether that exists or not and if it has advantages or anything, but could make sense.